Acceleration due to gravity and its variation. The acceleration due to gravity at a height h above the Earth's surface, assuming Earth to be a perfect sphere. Let g represent the acceleration due to gravity at the surface of Earth and g' represent acceleration due to gravity at a height h above the surface of Earth. G equals gm by r square and g' equals gm upon r plus h whole square. G by g' equals r plus h whole square upon r square equals 1 plus h by r whole square. G' equals g by 1 plus h upon r whole square equals g multiplied by 1 plus h by r raised to minus 2. That is, g' equals g multiplied by 1 minus 2h by r approximately, where r is the radius of Earth, h is the height above the Earth's surface, and g is the acceleration due to gravity. Thus, the acceleration due to gravity decreases with altitude. Variation of acceleration due to gravity with depth. Variation of acceleration due to gravity with depth is given by g' equals g multiplied by 1 minus d by r, where g is the acceleration due to gravity at the surface of Earth and g' is the acceleration due to gravity at a depth d. At the center of Earth, g' equals 0. Since h equals r, acceleration due to gravity at any point inside the Earth is proportional to the distance of the point from the center of the Earth.
Most people are familiar with the terms mass and weight, and might assume that mass is simply a fancy word for weight. In actuality, this is not the case, and the two terms have rather different meanings. To put it simply, mass is a scalar and weight is a vector. This means that mass has only magnitude, since it is a measure of an object's inertia, or essentially how much matter is present within the object. Weight, on the other hand, has magnitude but also direction, because it is a force, specifically the force that is exerted on an object by virtue of its position in a gravitational field. We will learn more about gravity later, but for now we can just operate under the common understanding that gravity is a force that pulls things towards Earth. Mass and weight are related in that they are proportional, and objects with more mass will weigh more than objects with less mass. But they are not the same thing, and when we discuss our weight in common parlance, we are actually referring to our mass. Weight can be calculated using Newton's second law, or F equals ma. Take an object like a 100 kilogram person. This value represents the mass of the person, which is more or less constant, barring any huge changes in diet, as it is a measure of the amount of matter in the person. But the weight of the person will depend on their location. On the surface of the Earth, the acceleration due to gravity is 9.8 meters per second squared, so their weight will be 980 newtons. On the Moon, acceleration due to gravity is about 1/6 of that of Earth's, because the Moon is much less massive, so the person will weigh considerably less as well. In the vacuum of space, far away from any massive object, the person will be essentially weightless, since there will be no appreciable acceleration due to gravity. In all of these cases, the mass of the person does not change, but their weight will vary depending on the presence and strength of a gravitational field. Since weight is a force, we will have to include weight in any free body diagram representing objects on Earth. This will be a vector with magnitude equal to m times g, pointing straight down towards the center of the Earth, where g represents the local acceleration due to gravity. We learned from Newton's third law that any force has an equal and opposite force, and so we will often encounter something called the normal force. The normal force is exerted by whatever surface the object sits on, and it points in the direction that is perpendicular to the surface. If this is a flat horizontal surface, the normal force will be straight up, opposite in direction to the object's weight. The more mass an object contains, the greater its weight, and the greater the opposing normal force. If these are the only two forces acting on the object, they will be equal and the object will remain at rest. Now that we understand the distinction between mass and weight, as well as the way that weight will be depicted in free body diagrams, we are ready to look at other forces that can act upon objects. Let's check comprehension. Thanks for watching.
Apparent weight and weightlessness. Astronauts who are orbiting the Earth experience the sensation of weightlessness. This is similar to the sensation you experience on a giant wheel or a roller coaster. To understand what causes weightlessness, an idea about true weight and apparent weight is necessary. True weight and apparent weight. The weight or true weight of a body is equal to the force exerted by the Earth on it. The true weight of a body of mass m is given by the relation W is equal to mg. The weight of a body is measured with the help of a weighing machine or by a spring balance. When a body is kept on the platform of a weighing machine, its weight is given by the normal contact force between the body and the platform of the machine. Similarly, when a body is suspended from a spring balance, its weight is given by the normal contact force between the spring and the body. When the body is placed on the weighing machine, the forces acting on the body are the force of gravity or its weight W acting downwards, the upward normal contact force N exerted by the platform of the machine. It is this upward normal contact force exerted by any supporting surface which gives a feeling of weight. This upward normal contact force is called the apparent weight of the body. The value of this upward normal contact force N depends upon the state of motion of the body. To understand the concept of apparent weight, let us imagine a person standing on a weighing machine placed on the floor of an elevator. Now observe the position of the pointer of the weighing machine when the elevator is at rest. When the elevator moves down with a constant acceleration. When the elevator moves upwards with a constant acceleration. And when the elevator falls freely. We observe that the apparent weight registered by the machine is equal to the true weight of the body, less than the true weight of the body, more than the true weight of the body, and equal to 0. That is, the apparent weight of a body depends upon the state of motion of the body. To find out why there is a variation in weight, click on the links provided. When the elevator is at rest, the person inside it is also at rest. External force is equal to 0. Therefore, the true weight of the person W acting vertically downwards is equal to the normal force N acting vertically upwards. In this case, the weighing machine registers the true weight of the body. When the elevator moves down with a constant acceleration A, the net force acting on the person is equal to true weight of the person minus normal contact force. N is less than the true weight mg of the person. Thus the scale reads less than the true weight of the person. When the elevator moves upwards with an acceleration A, net force acting on the person is equal to true weight of the person minus normal contact force. N is greater than the true weight of the body. Therefore, the scale reads more than the true weight of the body. When the elevator falls freely, that is, if its cable breaks, then both the person and the weighing machine fall with the same acceleration. mg is equal to mg minus n, or n is equal to mg minus mg, that is equal to 0. Thus, the apparent weight of a freely falling person or body is 0, that is, a person or a body appears weightless when falling freely under the influence of gravity. At this stage, the weighing machine will read 0. Thus, we see that during the state of weightlessness, the force of attraction due to gravity does not become 0. It is the apparent weight of the body which becomes 0 during weightlessness. Weightlessness in space. The spaceship and the astronaut orbiting the Earth at a certain height are actually in a continuing state of free fall towards the Earth. As a result, the astronaut does not exert any force on the sides or floor of the spaceship, and the sides or the floor of the spaceship do not push the person up. The astronaut therefore experiences weightlessness while orbiting around the Earth.
You slowly make your way to the top of that first towering hill on your favorite roller coaster. Your heart is racing because you know what's next. As you plunge, you feel dizzy and weightless, like you're defying the laws of gravity. But it's gravity that causes you to feel that way. Normally, the force of gravity pulls you toward the Earth's center, but the ground pushes back, keeping you in place. You feel this as weight. When you're in free fall, there's nothing to push against you. As a result, you feel a sensation of weightlessness. Astronauts experience the same effect in space. As the space station orbits Earth, our planet's gravity pulls it towards the center, but the station is moving fast enough that instead of falling down to the surface, it falls around the planet. This keeps it in orbit. Astronauts on the space station are falling along with it. So the next time you're screaming down a coaster ride, just remember, you're getting a small taste of what it's like.
பார்க்க போறோம். First application பாத்தீங்கன்னா dimensions of the heavenly bodies can be measured using the gravitational law. Like இப்ப எர்த் இருக்கு இல்லையா, அதோட மாஸ், அதுக்கப்புறம் அதோட ரேடியஸ், அதுக்கப்புறம் எர்த்ல ஆக்சிலரேஷன் டியூ டு கிராவிட்டி, இது எல்லாமே வந்து இந்த நியூட்டன்ஸ் லா ஆஃப் கிராவிடேஷனை வச்சு நம்ம ஹை அக்யூரசியோட கால்குலேட் பண்ண முடியும். நியூ ஸ்டார்ஸ் அண்ட் பிளானட்ஸை டிஸ்கவர் பண்றதுக்கும் இந்த லா வந்து யூஸ் ஆகும். சில டைம் வந்து ஒரு irregularities இருக்கும் இந்த மோஷன் ஆஃப் ஸ்டார்ஸ், அதை வந்து நம்ம ஊபிள் அப்படின்னு சொல்லுவோம். ஸோ இந்த ஒன் ஆஃப் த irregularity in the motion of the star வந்து என்ன பண்ணோம் அப்படின்னா lead to the disturbances in the motion of the planet nearby. ஸோ அது நியர்பை இருக்கிற பிளானட்டோட மோஷனை வந்து அஃபெக்ட் பண்ணும். ஸோ அப்போ அந்த கண்டிஷன்ல the mass of the star can be calculated using the law of gravitation. அடுத்தது இது வந்து helps to explain germination of roots is due to the property of the geotropism. இது வந்து ஒரு ப்ராப்பர்ட்டி ஆஃப் த ரூட், அது வந்து ரெஸ்பாண்ட் டு த கிராவிட்டி. இதையும் வந்து நம்ம நியூட்டன்ஸ் லா ஆஃப் கிராவிடேஷனை வச்சு நம்ம கண்டுபிடிக்கலாம். அந்த ஜெர்மினேஷன் ஆஃப் த ரூட்டை வந்து எக்ஸ்பிளைன் பண்ணலாம். அதே மாதிரி ஒரு ஆஸ்ட்ரோனாமிக்கல் பாடிஸ் லைக் பிளானட், காமெட் இதோட பாத்தை வந்து நம்ம ப்ரெடிக்ட் பண்ணலாம் இந்த லாவை யூஸ் பண்ணி. ஸோ இதெல்லாம் வந்து அப்ளிகேஷன்ஸ் ஆஃப் நியூட்டன்ஸ் லா ஆஃப் கிராவிடேஷன்.